All right, let's talk about thermodynamics. It's getting hot in here. So, thermodynamics is really just energy and heat and reactions. Chemistry, a lot of energy and heat moving around, right? We do talk about chemistry being the study of physical matter, but physical matter involves a lot of heat and energy transfers. So, involved in thermodynamics is enthalpy, which we'll talk about a little bit more. But the idea of enthalpy is super important. It's different from entropy. And then also, performing calorimetry is kind of the experimental way we're going to think about thermodynamics. So let's talk about work and heat. So work is moving things and heat is transferring energy. So if you think about a steam engine, I'm pumping in heat, and that is being translated into work, physical things moving. However, we also need to define the system and the surroundings. So the system is the thing we're looking at, and the surroundings is everything else. So you get to define the boundary for the surroundings in the system, but generally speaking, your reaction vessel is going to be your system, and everything else is going to be your surroundings. So if you're holding something in your hand, like if you're holding a flask, like a reaction flask in your hand is the surroundings, and the flask is the system. This becomes important later on. Energy is measured in joules. Joules are a derived unit. It's like kilograms per Newton second, something like that. That doesn't really matter. It's just joules. It's just joules. It's energy. In chemistry, we're generally dealing with constant pressure or constant volume systems. So when we're thinking about our system and our surroundings, we're not doing any work. We're not having work done on us. We're not doing any work. So we only have to worry about heat. So the symbol for heat is Q. And if heat goes into the system, we consider that to be exothermic. So if heat enters from the surroundings into the system, that is considered endothermic. And Q is positive. If heat comes out of the system, heat leaves the system, Q will have a negative sign, and that's exothermic. So heat is not, you can't have, like, negative energy is not a thing. The symbol for Q is telling you the way it is moving in relation to the system and the surroundings. So if we think about, again, if we're holding a reaction vessel in our hands and it is heating up, we are the surroundings. So what's happening there is heat is leaving the system and going into our hands, which we're perceiving as warmth. And so that system is exothermic because it's pushing heat into our hands, or heat's going into our hands. If you're holding something cold, like ice water, like a glass of ice water, it feels cold because heat is going from you are the surroundings, into the system. So it's endothermic. So the system is gaining heat and it's taking it from you, which you perceive as cold. So it's really important before you even try to do these problems that you understand what's the system, what's the surroundings. Because that definition is what's going to actually help you solve any problems that you're trying to solve. So system, surroundings, make sure you have them straight. Exothermic, heat is leaving the system. Endothermic, heat is entering the system. And again, we would perceive these, since we are the surroundings, we perceive these endothermic things as cold and exothermic things as hot, because we're the surroundings. So, specific heat capacity is something that is a value that we need to think about when we're doing work with heat. So our heat content is Q, and it comes up with the equation to find the heat content of anything, or the energy change for any system. We use the equation Q, the heat, is equal to C times M times delta T, where C is what's called the specific heat capacity. And the units are joules per gram degree Celsius or joules per gram Kelvin. That doesn't actually matter. I'll explain that in a second. But it is the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius or Kelvin. So for water, it's 4.184 joules, which says that you need to put if you have 1 gram of water, you have to put in 4.184 joules of heat, and that will raise the temperature by 1 degree Celsius. And these are all substance and phase specific. So liquid water has a different specific heat from ice water, has a different specific heat from steam. So this is not something, you can find this experimentally, which we'll look at, but generally speaking, this is something you're going to look up on a table. Now, the sea of water, you should probably memorize, because you're going to use it in pretty much every single thermodynamic problem you're working with. M is the mass, which is grams, and then delta T is the change in temperature. Delta anything is final minus initial, so delta T is T final minus T initial, so the final temperature minus the initial temperature. So, for instance, if something started at 25 degrees Celsius and warmed up to 35, you would say that the delta T is 35 minus 25, or 10. Now, here's where I mentioned that Celsius and Kelvin are interchangeable here, and only here. Only when you're using delta T, because if we convert 35 and 25 to Celsius, you get 308 to 298, and the difference between them is still 10. So you might see a specific heat in Kelvin, like joules per gram Kelvin. You don't have to convert to Kelvin. You'll end up with the same thing. So in this, and in only this case, unlike when we're dealing with gases, in this case, Kelvin, delta T in Celsius and delta T in Kelvin are the same. So they are interchangeable, specifically if you're talking about delta T. All right, so how do we use the heat capacity, right? So if we ask the question, how much energy is needed to heat 100 grams of water from 25 to 90? Q equals Cm delta T. So we plug in C of water, 4.184, mass of water, 100, delta T, 90 minus 25, or 65. Just plug those numbers in. Grams and degrees Celsius cancel, and you get 27,196 joules. That might seem like a really big number, and it is, and that's because water has a really high specific heat. So the specific heat of water is unusually high. So it's why it takes a lot of energy to heat up water, and why water holds a lot of heat, because it's got a really high heat capacity. If it takes 500 joules of energy to raise the temperature of 55 grams of a substance by 15 degrees Celsius, what is the heat capacity? So you can solve for heat capacity as well. So if Q is Cm delta T, then C is Q divided by M times delta T. So in this case, it's 500 joules divided by 55 grams times 15 degrees Celsius. Now, none of these cancel because you'll get the right units. You get 0.606 joules per gram degree Celsius. That's a more realistic heat capacity than most of the things. A lot of metals have heat capacities that are low like that. If a 75-gram block of copper that is initially at 98 degrees Celsius releases 1,500 joules of heat, what is the final temperature of the copper if the heat capacity of the copper is 0.385 joules per gram degree Celsius? All right, Q equals Cm delta T, so delta T is Q over C times M. So negative 1,500 joules because, the heat was released, it's exothermic, heat is leaving the system, so it's negative. So I'm applying a negative to it. This is very important. If you won't get the right answer if you don't put the negative there. So negative 1,500 joules divided by 0.385 times 75, and you get negative 51.95. Okay, so my delta T is negative because my copper cooled down, so that makes sense, right? The delta T is negative because it has a lower final temperature, right? So delta T is T final minus T initial, so T final is delta T plus T initial. So negative 51.95 plus 98, so my final temperature is 46.05 degrees Celsius. Okay, so it's a very straightforward equation, and you can rearrange to find whatever you want. The delta T can be negative. That's the only one. C cannot be negative, M cannot be negative, but delta T can be negative. All right, so let's practice. How much energy does it take to heat 45 grams of water from 20 to 50 degrees Celsius? All right, so Q equals C M delta T. So it's 4.184 times 45 grams times 30 degrees Celsius. You get 56,048 joules. 10 grams of a metal has its temperature rise by 22 degrees Celsius when 51.26 joules of heat are added. What is the specific heat capacity of the metal? So Q equals Cm delta T. So C, C is equal to Q over M delta T. So it's 51.26 joules over 10 grams times. Now, the temperature went up by 22, so this is delta T right here, times 22 degrees Celsius. you get 0.233 joules per gram degrees Celsius. Finally, what is the final temperature of 10 grams of aluminum at 25 degrees Celsius if 100 joules of heat are added? Here's the C of aluminum. So Q equals Cm delta T. Delta T is equal to Q divided by Cm. It's equal to 100 joules divided by 0.902 times 10 grams. And you find that that is equal to 11.1. And then remember that delta T is T final minus T initial. And so T final is equal to delta T plus T initial is equal to 11.1 plus 25 or 36.1 or 36.09.